Now that we've had a look at what the exponential function looks like, we're going to apply this to word problems because that's where the real purpose of even studying this one is. We're going to look at a couple of different versions of it. We're going to look at exponential growth. So that's when we are increasing our functions. So exponential growth, that's increasing. So remember when we drew that, that was our swoosh that went up like this. Okay. We're also going to look at exponential decay. So exponential decay is when it's decreasing. So that'll be when our swoosh is going down. Down here. That's when my swoosh is going down. Okay. In our word problems, we're going to have to worry about various bits and pieces. We're going to have to worry about our initial values, and we're going to have to worry about how it's changing and when it's changing. So initial values, well, those are just our y-intercepts. So when we were looking at those in our functions yesterday, we noticed that that was that y value in front of our function. So when I go to write a general function here, and I have my base of something, the exponent, my initial value, my a values, that was the a in front, right? So when I get questions with initial values, that's my y-intercept, that's the number in front. We're going to play with our bases. So these bases are going to be very important. The base is going to be equal to my growth or decay factor. So how much is it actually going to grow or decay? When we're talking about things that double, then our base is going to be 2. So we're going to be looking at the equation of 2 to the x. Tripling, same idea, right? Triple, instead of being 2 to the x, triple. That's going to be 3 to the x. We're also going to do a lot of increasing and decreasing by percent. So when I increase and decrease things by percent, well, I'm going to have to turn the percent into a decimal. And then if I'm increasing, then I'm going to do 1 plus that decimal. And when I'm decreasing, I'm going to have to do 1 minus the decimal. So what do I even mean by that? Oh my goodness, we need to get some examples in here to figure this one out. So let's say I have something that's going to increase by 5% every year. Well, I'm going to turn that into an equation. What I need to do with that 5%, and we're going to do this a whole bunch today, so we're going to get lots of practice by it. Our 5% is going to turn into 5 divided by 100, so that's going to equal 0.05. So then my base is going to become 1 plus 0.05. If I was decreasing by 5% every year, if I was going to decrease, so I still use that same decimal, but my base is now going to be 1 minus 0.05. Okay, and that's important. And when our questions are looking for what they call the growth factor or the growth rate or the decay rate, that's our decimal that we're talking about, 0.05. So that's our 5% growth rate. Or if I'm going down, if I'm decreasing, then the 0.05, which we just figured out was from our 5%, that would be our rate of decay, or our decay rate. Okay, so we've got a couple ways to word it. Means the same thing. Okay, so here we have a scenario. I'm talking about yeast cells in a culture. We have 5,000 yeast cells in a culture, and the number of cells are going to grow at a rate of 25% per day. So each of those pieces are important. The first thing we want to do is make an equation. So I'm going to say N is the number of yeast cells, D is the number of days, N with that little subscript 0, so that right there is a subscript, okay? That's what represents it as initial, and R is the growth rate. So to do this, I'm going to say that the number at a certain day is my initial number, bracket, 1 plus my growth rate, all to the exponent D, which is my number of days. So notice in the front here, this is my initial value. Inside the brackets, there's my growth rate. And because it's growth, I'm plussing, okay? And my exponent is how I'm counting time. So that's generally what we put up in the exponent. Okay, that's our time. So if I want to figure out how many cells there are a week later, so remember 1 week has 7 days. So that means I'm just going to sub in D equals 7, and then I'm going to use my calculator. I'm going to solve my question. Okay? So I want to know the number at 7 days. So my initial value, oh, we haven't made our equation yet. Oops, hang on. Sorry, let's finish writing our equation. So we've got our N at D is, my initial value is 5,000. So I'm told that's how many I'm starting with. I'm told that my growth rate is going to be 25%. So to turn that into a decimal, divide it by 100. So you get 0.25 as your R value, 0.25, all to the exponent D. So if I want to simplify that out, you can, you don't have to. I would say that my number at a specific day is 5,000 times 1.25 to the exponent D. All right, now we're ready to solve. Now I'm ready to figure out how many there are a week later. So that means 7 days. So my N at 7 days is 5,000 bracket 1.25 to the exponent 7. Let's calculator that first. Do not do the 5,000 first. You have to calculator this part first. If you do it in your calculator all in one step, it's usually fine, but not always. So when we go to calculate that, let's see what our answer is going to be. So you end up with 5,000 times, what's that, 4.7, oh my goodness, that's a big number, 4.768 times that by 5,000, and you get approximately 23,841. And because this is a word problem, we should always finish off with a therefore statement. So, therefore, there will be 23,841 yeast cells after 1 week. Very good. Okay, so there's just a final snapshot of our picture. We figured out our initial value. We figured out our growth rate, so we added that to 1 because it was a percent. We popped in 7 and we calculated it to get our final answer. Let's try another example. So let's figure out Canada's population. So if we Google this, so let's pop it up. I just typed in Canada's population growth, and it is currently at 1.4%. So it's changed over the years. Some years it's more, some years it's less. We are currently at 1.4% annual change. So I'm going to write that in there. Our current population growth is 1.4%. Okay. And what's our current population? We have a current population of 37.06 million. So that was in 2018. So let's go with that number, 37.06 million. 30, what did I say? 37.06, right? 37.06 million. So that's 2018, just because those are the stats available. So how many people will there be in another 100 years at that growth rate? Let's figure that one out. We can definitely do this. All right. So let's remember. Let's see. Since I'm going to use population, I'm going to say let P represent population. I'm going to let T represent time in years. Okay, so we can create an equation. Oh, and P with the little 0 at the bottom, that's going to represent my initial population. Initial population. R is going to represent the growth rate. Okay, so let's figure this out. So my general form for my equation is P at T equals P with the little 0, so that's my initial, times, I'm dealing with percents and I'm growing, so I'm going to plus my rate to the exponent T, because that's how I'm going to count it all. So let's see, using our values, my initial value is 37.06 million. 1 plus my growth rate, so percent, divide that by 100, move your decimal place 2 times, 0.014. 0.014, that doesn't sound very big, does it? Let's see what it does. To the exponent T, so there's my equation. And then I want to figure out what it's going to be like in 100 years. So I'm going to make T is equal to 100. 0.06 bracket 1.014 to the exponent 100. Let's calculator it and see what we get. All right, so type in your calculator that we need to do I've got 37.06 times 1.014 to the exponent 100. That gives me 4.016. Times that by 37.06, and we end up with, oh my goodness, 148.83. Remember we said that was in millions, so therefore in 100 years, so, oops. I don't know what just happened there. So in 100 years, so that'll be the year 2118. The population will be 148.83 million. So it'll be 148 million people living in Canada at the current growth rate. That's a lot of people. So here's a great example of exponential decay that you experience every day in your new life. You've bought a beautiful vehicle, you have to pay some kind of initial price, fast forward about 5 years, and what's your vehicle going to be worth now? So internet's full of this stuff too. If I type in new car depreciation, let's see, oh, look at these beautiful looking exponential curves. Oh, that's so nice. Let's see. According to our averages here, oops, I got lost. Its averaging decrease is 20 to 30% by the end of the first year. From years 2 to 6, depreciation ranges from 15 to 18% per year. So that's a lot. That's a huge depreciation. So let's pretend we bought a vehicle for, I don't know, $30,000. So let's say we bought a vehicle for $30,000. Fast forward 5 years. So let's see, do you want to even just do 1 year? Let's just do 1 year. That was huge, 1 year. So remember we said that we were losing, let's go with the maximum here, 30% depreciation. So that means it's going down. So let's figure out how much that's going to be worth. All right, we got to create our equation. So we're going to need some variables. So let's say maybe let, I don't know, P for price. Let P represent price. We're going to let T represent years. P with the little 0 is my initial price. T is years. P with the little 0, so that's P naught, is the initial price. And let's not forget R. So in this case, R is going to represent our decay rate. So let's create our equation here. So P at T is going to be equal to my initial 1 minus my rate because I'm decaying to the exponent T. So P at T is going to be equal to my initial value. So we figured that one out. We're going to just assume it's a $30,000 vehicle. 1 minus, so I'm going down by 30%, so divide that by 100. So my R is going to be 0.3. All to the exponent T for time. So after 1 year, so we're going to put 1 in for T, 30,000 bracket, that simplifies to 0.7 to the exponent 1. Throw that in your calculator and let's see, we've got 30,000, 30123, times 0.7, 21,000. So after only 1 year, your vehicle went from being a $30,000 vehicle to a $21,000 vehicle. What if that decay rate was going? And let's figure out after 5 years. So same equation. Let's say it's the same depreciation rate for 5 years, 30,000. And this time it'll be 0.7 to the exponent 5. So let's type that one in. So 0.7 to the exponent 5. So we're going to have 30,000 times 0.16807. Finish it off, times that by the 30,000. And that, after 5 years, after paying all that money, because 5 years is about when you're done paying for it, it's only going to be worth $5,000. So therefore, your $30,000 vehicle is worth $21,000 after 1 year and $5,000, $42.10 after 5 years when depreciating at 30%. Well, that's kind of sad. Okay, so just to finish it off, let's look at example 4. So here I'm giving you 3 different equations, and I just want you to interpret them and tell me what you see. So I want to figure out the initial amount, I want the growth rate or decay rate, and then I want to know the number of growth or decay periods. So that's what the number in the exponent is, like how long are we doing this for? So let's look at the first one. So let's remember that the initial amount is the number that's in front of the bracket. So in each case, my initial amount is in front. So my initial here is 300. My initial here is 10,000. And my initial here is 25. Okay. My growth rate or decay rate, so that I have to look inside the brackets for it. And remember, when we're dealing with percents, a growth rate would be 1 plus R, and our decay rate would be 1 minus R. So let's look at this first one here. So my growth rate, I have to get bigger than 1, so it's definitely a growth. And how did I get it? So let's see, R will be equal to 1.03 minus off that initial 1, so you get a 0.03. Turn that into a percent. So to turn it into a percent, let's times it by 100. So that's going to be 3%. Let's look at this one. So in here, we've got R is going to be equal to 1.5 minus 1. So 0.5, turn that into a percent, times it by 100. So my growth rate here is going to be 50%. And let's look at the last one. Notice how I've now got a minus sign in here. So that means I'm going to be a decay. And I don't even have to subtract anything because it's already separated for me. So in this case, my rate is going to be 0.02 or a decrease of 2%. Good. Okay. Last piece, the number of growth or decay periods. So that's my exponent. So in this case, my number of periods will be 7. For this one, it's going to be 10. And for this one, it's going to be 12. So that's how we interpret our equations. So all in all, I think you're ready and set. Go try a few word problems on your own and let me know how it goes. Well done, guys.